Large language models do not understand the world. They do not possess consciousness, and they do not execute logical thought. Strip away the interface, and you are looking at a mathematical approximation function. An LLM operates as a high-order Markov chain, relying on a strict conditional probability equation. The architecture takes a sequence of historical data and calculates the statistical probability of the next token. To understand exactly how these systems function, we will break open the architecture. We will cover the mechanics of self-supervised pre-training, trace the mathematical flow of architectural masking, break down the sampling algorithms used for decoding, and finally expose the mathematical roots of AI failure states. The magic of AI is brute force mathematical probability executed at a planetary scale. To acquire human language, models undergo self-supervised pre-training. The system scans trillions of sentences, artificially masks future words, and attempts to guess them. Because the text itself acts as the label, there is no need for manual human annotation. First, the raw text is sliced into individual tokens. These tokens are mapped to numeric IDs and then embedded, transformed into long mathematical vectors that plot their exact semantic coordinates in high-dimensional space. As the model processes the sentence step by step, it uses the accumulated context of the previous vectors to predict what belongs in the next position. We represent the actual, correct next word, the ground truth, as a one-hot vector. In an array of 50,000 possible vocabulary words, only the correct slot receives a value of exactly 1. Every other slot is 0. The model's raw prediction comes out through a softmax function. It outputs a fragmented probability distribution, spreading percentages across thousands of competing words. This is the cross-entropy loss formula. We use it to measure the exact mathematical distance between the model's uncertain guess and the absolute certainty of the ground truth. Because the one-hot vector is mostly zeros, it wipes out almost the entire summation. The calculation collapses into a single result, the negative log of the model's predicted probability for the correct target word. The primary goal of the training phase is to force the neural network's weights to constantly adjust, pushing the target probability toward 100%, which drives the loss distance down to 0. Executing this exact mathematical penalty trillions of times forces the system to adapt. To guess the correct words consistently, it has to absorb the rules governing those words. By relentlessly minimizing mathematical loss across a massive corpus of text, the network implicitly constructs an accurate map of human grammar, logic, and facts. There is a strict mechanical divergence between how a language model is constructed during training and how it is later deployed to users, a phase known as inference. During early training, a model is highly inaccurate. If it makes a wrong guess early in a sentence and uses that bad guess as the context for its next prediction, the error compounds. This error propagation causes the entire subsequent sequence to derail into total nonsense. To prevent this during training, we use teacher forcing. If the network generates an incorrect token, the system immediately intervenes. It throws out the bad prediction and forces the correct ground truth token into the sequence before the network attempts the next step. Because we already possess the full text and know the correct answers in advance, teacher forcing allows the hardware to calculate the loss for every token simultaneously. This parallel processing makes training on massive GPU clusters physically possible. But in production, during inference, the teacher is removed. The model is entirely on its own. It must rely on autoregressive generation, operating in a rigid step-by-step loop. The first generated token immediately becomes the input context for step 2. Teacher forcing provides the stability and parallel computing speed necessary to build massive architectures. Sequential autoregression enables the continuous, autonomous creation of novel text. The structural difference between the major AI architectures is entirely governed by attention masking. This is the mathematical rule set dictating which tokens are allowed to share information with each other. In an encoder-only architecture like BERT, the flow of information is bidirectional. A token can look at every single word that comes before it and every word that comes after it. Bidirectional flow is perfect for deep reading. If a word has multiple meanings, the model relies on the surrounding context on both sides to accurately isolate its definition. Bidirectional flow fails for text generation because it allows the model to cheat by looking at the answer. It learns no predictive logic. This formula contains the mathematical solution for generation, the causal mask matrix. We inject a matrix containing negative infinity values into the attention equation. When those negative infinity values pass through the softmax function, they are mathematically converted into absolute zeros. This physically cuts off the information flow. The model is intentionally blinded to future tokens, forcing it to generate text based strictly on past context. This creates the decoder-only architecture. We also have the encoder-decoder architecture, like T5, which is a hybrid model engineered heavily for tasks like language translation. It uses cross-attention as a bridge. The encoder reads the full input bidirectionally to capture the complete context, and then the decoder pulls from that rich context while generating the output causally, one blind step at a time. Modern generative AI is entirely dominated by decoder-only architectures. Their causal masking aligns the mechanics of their training with the sequential nature of their deployment. The specific rules of mathematical masking decide the system's core capability, analyzing existing context or inventing novel sequences. When you submit a prompt containing examples for the model to follow, it does not trigger backpropagation. The base weights of the neural network remain entirely frozen. Instead, the model uses in-context learning. Your prompt creates a temporary gravitational pull within the hidden activation states, forcing output tokens onto a specific trajectory. Once the internal layers process this trajectory, the final output layer calculates the raw logits, and the system must pick the next word. This requires a decoding algorithm. The simplest approach is greedy decoding, which strictly chooses the token with the highest mathematical probability. But this deterministic approach leads to repeating patterns, as the math can force the model into an infinite recursive loop. To fix this, we use temperature sampling. This is the mathematical slider for creativity, represented by the tau variable in the probability equation. If we lower the temperature towards 0, the mathematical gap between probabilities is exponentially magnified. It creates a steep cliff, crushing alternative options and forcing the model back into a rigid, highly logical greedy choice. If we raise the temperature above 1, the probability gaps are mathematically flattened. Obscure, lower-ranked tokens gain a chance to be selected. This unpredictable sampling sparks variety, though pushing it too high generates complete nonsense. What we perceive as AI creativity is the result of a deliberate, mathematical flattening of a probability distribution. To evaluate these systems, engineers use the MMLU benchmark, a massive, multidisciplinary test spanning law, medicine, and economics. It proves that massive models encode complex human knowledge rather than just mastering conversational syntax. But this knowledge base creates a paradox. A large model trains on 15 terabytes of human history, but compresses that entire dataset into a file size of just 140 gigabytes. Because of this extreme, lossy compression, models cannot store raw text files. They only store statistical relationships between concepts. When you prompt it, the model is dynamically reconstructing data based on those surviving relationships. This is the mathematical root of hallucination. The loss function we use to train the system optimizes strictly for smooth string probability. It has absolutely no mechanism to optimize for objective reality. If the vectors for famous physicist and optical invention sit too close together in the high-dimensional space, the model's attention mechanism can easily cross wires, confidently outputting a claim that Albert Einstein invented a specific historical device. The output will be syntactically perfect and statistically plausible. The model fulfilled its mathematical objective perfectly. The sentence just happens to be a complete lie. We compound this issue through reinforcement learning from human feedback. Because human graders naturally give high scores to AI outputs that agree with their own biases, the algorithm learns that flattering the user's false premises maximizes its mathematical reward. This results in sycophancy. We have engineered a high-precision probability engine. But by prioritizing syntactic perfection and human approval over objective truth, we have created a mathematical reflection of our own information, not a reasoning mind.